Hi, I'm Paul Bennett, and I'm a researcher at Microsoft. And today, I'll be talking to you about research across Microsoft, improving search and recommendation. Research that is not only pushing the boundaries of the state of the art, but impacting our products and changing our notion of what is possible. Now, when I say search to you, what is it you think of searching? If you're like many people, the first thing that might come to mind is the World Wide Web. And maybe if you're like me, you might go to Bing to search there. Search, though, is much broader than the World Wide Web. In fact, search is across all of Microsoft. Windows search is a place you go to search for apps and your personal files and devices that help you do the work you do every day, or play. Find all of your personal files. LinkedIn search, you might go there to find a job, or recruiters might go there to find you. Azure Cognitive Search, a service where we help businesses and organizations provide the top search to their customers and people at their organizations to empower them. Outlook search to help you find your email. In this hybrid work environment, team search is ever more important as you search over chat messages, meetings, and other files that are stored in Teams. Important not just at work, but also school as well. Xbox search, where you can search for new titles to play and other things that discover new ways to have fun. And even code search, where on Azure DevOps, you might find the code that you want to edit if you're a developer, put it in the context of other people's work, and understand how you do your job most effectively. Search just isn't in Microsoft. It's across the whole world and touches all sorts of surfaces. You'll see this show up in places like if you're a lawyer or you work in the legal field, you might go to the US Patent Office and search on their site for patents. If you work in the biomedical area, you might go to someplace like PubMed and search for scientific articles. Now, the interesting things about both of these, if you work in the legal or biomedical fields, say you work in an enterprise, you can search externally, but you have the same search problems internally, where you're going to search over legal documents or biomedical documents, often with very technical and different phrases than what we see on the open web. And a key part of helping you do your job is understanding how that language means what it means in the technical context and not more broadly in the web. You might even see it crop up in other cases. So popular places like Pebble Go for education that your kid's teacher might choose to have your kids use for education. The search there is going to impact how well your child is able to discover the resources they need. And you'll even see it cropping up for social impact. So open source for social good is an effort where you can go to places like Ovio and find projects where you want to contribute your skills as a developer, a project manager, or simply an innovator to help projects for social good impact people dealing with hunger, relief, and a variety of other causes. And we care not only about those problems that are first party, where we try to put better search into Teams and Outlook and Bing. We also care about those third party cases where we try to provide the best search through Azure Cognitive Search, and even these impact for social good. Here I've shown a reference to one of the papers where we're trying to understand what are people's motivation for open source for social good, and how do we provide better matching of skills to projects so that we can help the world throughout society as well as within Microsoft. So why is search not a solved problem? Now, if you think of this first with web search in mind, your first reaction is probably like, well, I found the thing I was looking for today. But as you get to rarer type of needs, less common cases, you're searching for things for a specific need. Even on the web, it's not solved. And when you expand to all of these other cases, you realize search still has a ways to go. What's at the fundamental reason for this? Well, search engines across all companies perform best when there are logs showing past queries and documents and how people interacted. And whether those are completely done in a privacy-preserving way where you can't see the logs, but you can learn from them automatically, the algorithms you deploy, or in cases where you're able to gain some insights from behavior. In either case, the AI does best when there are these massive search logs. But it turns out many key scenarios lack search logs. There are emerging verticals. There are cases where there are low resource languages. These are languages that aren't targeted first in terms of where businesses first put their effort in development. Enterprise search, email search, the list goes on and on. And we at Microsoft would like to bring the best of technology to every one of these scenarios. So what is the fundamental problem? The problem is that while we made great progress in understanding content using AI-based methods, we still have a ways to go in understanding content, queries, and people, and how to bring the most relevant results throughout search and recommendation. And I'd like to share with you an aspiration we have. Our aspiration for universal search and recommendation. We believe high-performing search should not be limited just to web search. We believe in bringing these offerings to every business, small and large, every organization, whether a nonprofit or for-profit, every case of people using one of our products. Throughout those cases and extending to greater impact for society, we would like to bring universal search to them. And what we mean by that is we want to provide push-button customized search and recommendation that works for any person, any vertical, and any data. Now, the challenges in this space have been large because each different scenario deals with different types of data, different types of people, different search stacks. Now, the great part is we've actually had progress in this. As we make more progress in understanding content directly with AI models, we're able to bring technology that first maybe improve the web into other scenarios and learn more how they adapt automatically and even universally apply. And so what I'm going to tell you about today is a few trends toward universal search and recommendation. Now, you're going to hear more about many of these things later in the day, and you'll hear about them in detail. So I'll just touch on a few highlights. There are 4 key trends that I think about that are happening now with universal search and recommendation. And here I'm just going to go a little bit into the first one, dense retrieval based on representation learning as the foundation. And what's been needed here are both gains in efficiency and accuracy to make dense retrieval possible. What is dense retrieval? If you just use a search engine, this may make no sense to you. A basic search engine classically would take the set of words that you type in that search bar of the query and look to see if those words occur in different documents on the web. Now, if you have many, many documents, 1 trillion documents, you need to do that extremely fast. So having effective search is all about searching those documents without having to look at every one in a pure scanning fashion, and yet still finding all of the relevant ones. So the classic ways of doing this would take what was called a sparse representation. They would only represent each document in terms of the words it contained. With advances in deep learning, AI models can now take and learn to represent and compress that content into a vector, a series of continuous numbers. And this represents the content that's in that document. What this then allows you to do is consider other methods, dense retrieval methods. Now, dense retrieval methods were explored for a long time, but often thought to be too inefficient. And even when people were able to make some gains, they weren't able to have accuracy gains on par with sparse indices. So the interesting thing is that the science that we've pushed forward at Microsoft has been able to make progress on both of these, where we now have dense retrieval actually in production in Microsoft systems and impacting a larger variety of surfaces. Furthermore, there's a great runway of research ahead. So I'd like to just briefly take a look at the search landscape and think about how technical advances have looked over time. If you think about web search and limited other scenarios, and these other scenarios are cases where you have a lot of resources to throw at it, you can afford to say, here's 100 people, go solve this problem. In those cases, you can actually develop a very customized stack for the scenario. And what we saw there is, from the 1970s to the 1990s, the primary things were bag of words representation. This is a case where a document is represented as the set of words that are in that document in no particular order. The matching function that was used, BM25, is based on a probabilistic model of relevance. It started to be invented in the late 70s, kind of got tuned in the 80s. Some further advances on that as we came into the late 90s with BM25F. But primarily, for 30 years, 70s into like the mid 90s, we're talking about a classic bag of words approach. From 1990 to 2000, we started to see what are classic information retrieval features. These are cases where people tried to identify by hand things that would add a signal of relevance and help you determine inverse document frequency. How rare is this word in this corpus? And then there would be arguments like, should we take the log of that, or should we have it in the normal space without log? And this is what research looked like in that time, where you tried to identify these specific features that would work and then simple combinations of them. That moved into the 2000s, where we started to see learning to rank, and machine learning started to come into information retrieval and say, hey, we don't have to have simple combinations. We can learn combinations of these features. Still, we were exploring a variety of features and then ways to improve the algorithm to learn to rank. As we came from 2010 to 20, we started seeing neural IR, where neural models, not just for ranking, but for representing short pieces of text and doing matching. And finally, as we arrive to the current day, we see dense retrieval. And this is where we see the present and the future happening. More representations of content as vectors and how to leverage them. Now, if you look at most other scenarios still use bag of words in BM25, and you'll see these show up, until recently. Azure Cognitive Search was largely dependent on that, and we've had a series of advances to bring the same kind of innovation into Azure Cognitive Search. Lucene, Elasticsearch, Solr, a variety of things that you see in the external world still primarily depend on this. Why? Because the fundamental challenge of solving things universally has been hard to make progress on. So there's these decades of gap. And to briefly go through 3 breakthroughs, we've made gains not only in efficient searching, but also in short text matching and in understanding the full document content. Now, eventually, we'll extend that type of content representation to other things. Video, image, even things like representing drugs for drug discovery. If you want to do a medical test, how do you compare one drug to another using just a vector representation? All those things can accelerate how you actually search for and find relevant information. And that's some of the active research that we have going on, understanding representations across all types of content. So when we think about efficient, dense retrieval, the primary thing that it relies on is called approximate nearest neighbor. And this is the idea that a query comes in. Now you convert these words into a representation as a vector. You now want to actually go and scan all of the matching items, their vector representations, and see which is most similar. I've already said you need to do this fast. You can't do a scan, so you need sublinear performance. So 2 advances at Microsoft, SPTAG, Space Partition Tree and Graph, gives us some gains there. And then disk ANN, which leverages disk memory architecture, also helps us solve these problems. How? In SPTAG, they rely on a clustering to cluster nearby items, and then a KD tree allows you to quickly find which approximate clusters are the right ones. Within those clusters, there's a graph structure that allows you to quickly find the similar items. In disk ANN, the trade-off between memory architectures of RAM and SSDs, which are faster disks in terms of reference allocation, allows you to quickly look up the items that you need. Now what this looks like is you start with a very dense graph that comes from how similar items are to all of the other possible items. And then you learn a sparse graph representation. And as you pare it down, eventually get to a place where you can store all the compressed vectors in RAM while the graph itself is sparse enough to be on the SSD and have relatively fast memory of references. Breakthrough number 2, short text dense retrieval. And this relies on matching very short pieces of text. This is a thing like matching a title to a query or add text to a query, very short text. And so gains there started with advances like DSSMs and continue to this day with extreme classification. And so for those who are interested, paper at ICML this year looking at extreme classification, where you learn over hundreds of millions of labels by implicitly associating labels with how people have clicked on previous documents, and learn an embedding for that can be leveraged in this short text matching. And these have had extremely large impact in relevance throughout search and advertising. So how do we think further within the short text world of matching? Well, what you can think of this as is having two deep models, two transformers, compute a representation of a query or any short text field. And the most common short text fields are often called AUTC, anchor, URL, title, clickstream. Clickstream is all the previous queries where somebody has clicked on this document. So for any of these, you can compute the representation, just compute a feature that says how much they match, or directly use them within dense retrieval by layering ANN on top. The final breakthrough I'll mention is in full body vectorization. You want to go beyond short text and understand the full content. And in this case, by understanding the full content, what are the gains? So here we've had a research advance just published this year in ICLR called ANCE, Approximate Nearest Neighbor Negative Contrastive Estimation. What does that complicated phrase stand for? It means a better way of learning what is relevant and what is not in order to understand the content fully. What do we get and what does it mean to you? It means in Bing, we can understand the content as a vector across all of our documents, not just short text, and automatically match them. What does this mean for universal search? Because we're focusing on just understanding the content, we're able to carry this over to scenarios beyond the web that only have content available and represent them. Not only do we get large gains in recall from this, we actually get massive system improvements, up to 2 times improvements in the serving costs based on previous systems that we've used. What does the research path look like to something like this? So the interesting thing is, if you know the field of information retrieval, from 2010 to before, there were many attempts in the information retrieval community to leverage learned representations. These looked at things like latent semantic indexing and latent Dirichlet allocation as dense representations, and trying to bring those into information retrieval to improve the state of the art generally were failures. They'd give maybe minor gains, but never enough to be worth the complexity. From about 2014 to 2016, there was a period of excitement around initial word embedding models like word2vec, in an effort to try to leverage those to gain improvements. As people failed to gain improvements within search, a pessimistic view in the literature often developed that we would never get those kind of gains. And some people moved from doing full retrieval with the dense model to just saying, maybe we can just actually expand small words and do that at a re-ranking level, where we take the top 10 or top 100 documents and take the dense representation there to slightly improve things. That kind of approach was actually successful in 2018, where people took BERT to do this soft re-ranking approach and give a small gain. Still no particular gains within dense retrieval to be able to search the entire breadth of the web in a semantic way. In 2019, we started to see actually some success in dense retrieval with representation learning in very limited cases, like OpenQA and phrasal-based matches. And so there became questions on whether one embedding would actually work for document retrieval. And then that brings us to 2020, where we identified the key problem was actually in the selection of negative examples of what was not relevant. Because when you learn automatically what is relevant and not, you have to have a good example not just of what is relevant, but what is not relevant. So to give a little more intuition why dense representation for text retrieval is hard, intuitively speaking, you can look at a case where we have at training time a set of queries and the documents have been labeled as either not relevant, here shown as 0, or relevant, shown as 1. So if you just label some documents as relevant and some as not relevant, it turns out, because of the large size of collections, there are many irrelevant documents. And so what the algorithm sees as irrelevant is not nearly broad enough, nor distinguishing enough from the positive. What you really want to find are the most informative examples of not relevant, which are the things very close to relevant and yet not relevant. So this sample is not representative, and so the model that you learn, when you actually try to apply it in practice, tends to not work very well. Well, if you do machine learning, you say, that's fine. I know how to fix that. I just go out, it's a large collection, I can pick documents at random and have the assumption that on average, those documents are irrelevant, and they'll serve as my example. And so yes, we can try that. The problem is that when you choose documents at random, they're actually often too easy. Yes, they're negative, but they're so far from the relevant examples, they don't provide a strong signal for learning. And so the key is to say, how do you sample more intelligently? So here what you'll see is a two-dimensional representation of the distance that ANCE learns. So it's been projected down to 2 dimensions, so it's easy to visualize. Here the star is a query. And what you see are the positive green pluses are right near that query. If you sample negatives randomly, you end up with all of these gray dots. Those are much further away from the query. Yes, they're negative, but they're far away, and they don't help you learn that boundary that you need. If you sample in a weighted fashion using some estimation of relevance like BM25, you get the examples like the yellow triangles. Again, negative, but much further away from the boundary. If you actually use the dense representation to sample, you start to get things actually close to the boundary, so that when you retrieve that point, if you imagine that dashed circle as the things nearby in the space, you tend to mainly get the positives. Now what happened? Did I just assume I had the dense representation in order to get the dense representation? Yes, kind of. What we actually do when we're training that model is use the current dense representation to find a set of negatives. And you can think of it as shrinking the space and finding harder and harder negatives. Now, what's so hard about that? Well, when that scaling dense representation is already hard and you're going to involve it in a learning algorithm, now it's even harder because you're going to run this multiple times just to train this. And these are some of the challenges that we solved in that paper. For those who want to read more of the technical details there, as well as the theoretical foundations, I invite you to go read that paper. Now, let's return to that question. So it improved the web. Does it really improve anything else? And so we went and looked at 3 different query workloads, representing different types of people and different types of corpora that they search over. Developers who might search over API documentation, gamers who might search over gaming-related needs, either within a game or externally, and biomedical professionals who might search over biomedical corpora like PubMed. And in all of these cases, what we found out is not only did ANCE outperform classic algorithms, we could actually combine them to get something even better. And this was without even customizing it further. So truly a step towards universal search and recommendation. And so when we think about that vision more generally of universal search and recommendation, we see ourselves as pushing on 3 fundamental technical challenges. The accuracy, we will always need better relevance of search and recommendation. The generalizability, we need one solution for all search and recommendation scenarios. And the scalability, we need to be able to index and serve at scale, not just because of the size of the web, because it enables us to bring these offerings to more and more people across different types of businesses and organizations, and allows them to choose the scale that fits them. This representation learning is one key part of this scenario. And we think about learning representations across these modalities in one learned representation space. But it's not the only key to finding the solution. Within representation learning and search, we not only think about the fundamentals I've talked about, but as we think about new breaking areas like multimodal representations, can we jointly model the semantics of image, text, and video? Can we extend those to those far-reaching cases? I've given a few references here, which I invite you to read more on if you want to know more of what's happening in the multimodal space. When we think about actually learning across users and interaction, right? Data is connected in various ways. Sometimes it's through links, sometimes it's based on how you use 2 things in conjunction. And so graph learning gives us the ability to leverage content and the connections between data together in order to learn across different users in the certain scenarios or within a user. We can learn across the connections you have between documents based on how you use them. Within an organization, we can use the structure of the organization to actually aid how we learn search and recommendation. And a few of the references I've given here, I've talked about how we think about actually modeling a user's interest so we can find the most relevant items to them. As we involve composite embeddings that take graph-based neural networks and learn how to update quickly what the representation is we have of the user. We also consider privacy-sensitive learning scenarios so that we can make sure we uphold our guarantees of privacy and how we handle our customers' data, as well as how we think about bringing knowledge more deeply in and connections that we have in knowledge graphs. Finally, we think about causality and robustness. How do we make AI models that work well in every scenario. And so here we see gains from causality methods that allow us to learn things that are not just an artifact of this particular data set, but rely on more fundamental mechanisms and interactions between the data. These more robust models allow us to carry over from one language and country to another much more reliably. As we progress these models even further, we see a future where this technology helps our customers carry over their businesses from country to country, from market to market, and from scenario to scenario. Again, I put a few references at the bottom where you can pursue on your own some interesting recent developments on causal learning. Finally, when we return to this vision of universal search and recommendation, I hope you will join us on this journey, whether you're a researcher, a customer, or just someone interested in learning more, as we look to provide push-button, customized search and recommendation for any person, any vertical, and any data. Thank you.